Hello, my name is Narayan Gusal. I am going to discuss about my class project that on title Optimal Control of Energy Storage System in a Microgrid. First of all, let's start with introduction. Due to environmental concern and various benefits, the integration of renewable resources is increasing rapidly. However, the intermittency of this type of renewable resources are a great challenge to modern distribution system. The energy storage, which is expensive, but it is the best way to promote the renewable energy and its intermittency. However, the installation of the large or inappropriate size of this energy storage system can cause energy waste and increase the cost of the system. For this reason, energy storage system energy management is essential for the control and operation of a microgrid. To manage the operation of energy storage system, various centralized control algorithms have been proposed, and with the information of all the nodes are required, which is so expensive and difficult to control and collect. It will cause various problems like a single point failure. The distributed optimal control algorithm, in which local information and its neighbors information are collected, thus enable the sharing of computation and communication burden among the local controller to significantly reduce the investment for sophisticated network or centralized control. There are two layers basically in this distributed control algorithm: the outer layer and the inner layer. In the outer layer, in this case, the SOC management is performed for the state of charge. The outer layer can be respond to the dynamic electricity price, which is used to help reduce the customer electricity cost, and it calculates the reference for each energy storage system. The inner layer is cooperative control strategy, which enable each energy storage system to achieve its reference SOC value in an optimal way. The proposed distributed optimal control can minimize the difference between the present state of charge value and the reference state of charge value for each energy storage system, control the energy cost, and maintain the system demand balance in a microgrid at the same time. Let's go to system modeling and problem formulation. Basically, microgrid is interconnection between user load, distributed control, and energy storage system. For this case, in this figure shows a very simple 5-bus microgrid. In each bus there are energy storage, load, and local distributed generation. For each this bus, the energy balance should be maintained, that is Pg minus PL minus Pb plus Pu. For each these are terms are Pg is the local distributed generation, PL is the local load, Pb represent the energy storage system power, and Pu is the power supplied from the main grid. When there is not enough power, then power will be supplied from the main grid. If the Pb is negative, that means batteries are discharging its power to the system, and if Pb is positive, then the batteries are charging. To prevent the damage and prolong the life of energy storage system, the state of charge of these energy storage system should be maintained within some limit, that is this should be maintained within 20 to 80%. So with this equation shows this limit SOC min minus SOC min to SOC max. So this is the dynamic equation of energy storage system. We can see from there SOCT plus delta is SOCT plus SOP dot ut and delta. SOCT is the vector of energy storage system in short time interval. Interval delta B is the topological structure, which is taken as identity in this case, and ut is a vector of control variable. The main objective of each here is to minimize the effort for controlling energy storage system and keep the track of energy storage system SOC level. So the objective can be described in this way. In this equation, in this third equation, the first part is the error in the final state, and in second part there are two part actually. The first is error in the time interval t0 to t, and second this part is the total power consumption for controlling the energy storage system of all nodes, that is to make the state of charge of each is each energy storage system to its reference value, and Qt and RT can be used to regulate the weight of static SOC error and power consumption and so on. Let's go to distributed optimal control algorithm. There are two layers basically. The first is SOC management for energy storage system. In this layer, assume that the user have preferred price threshold based on their requirement and price, that is P min to P max. The SOC reference can be calculated from this way. SOC reference will be SOC min if the PT, the price of time of use price, is greater than equal to PU max, and PT SOCI max if the PT is less than equal to PU max, and SOCT otherwise, in other case. So after this SOC reference, the distributed optimal control method in the internal layer is proposed to control the present state of charge to achieve its reference value in an optimal way in a given time period. So the second is the distributed optimal control. The objective of this layer is to optimal minimization of the difference between the SOC and SOC reference value and minimize the controlling power consumption that is needed to make the state of charge of this battery up to its reference value. So objective function is as before. So dynamic state of charge equation can be written in this way: SOC dot is equal to B and UT, B dot UT. Thus the performance index for some agent I should have the penalty factor this term, or Ni the set of the neighboring node. From all this analysis we can find this long objective function, this first part and this second part, and finally this same and this second part as previous one. In these equation, m n k all are greater than equal to 0, r capital R is equal to small r, and in small r is greater than equal to 0 is scalar, and in is a n-dimensional identity matrix, r is a weight of the control variable I, and q is ml square plus nl plus kin. To exist this optimal control, n square minus 4mk is equal to 0 for m n k must satisfy. After simplification we can guess this equation for distributed optimum controller. You can see in this equation there are two these terms and these terms. This algorithm only require the local and distribute neighboring information to update the controllers. We don't need the information of all the systems, just need the information of the local nodes. So this figure show the interconnection between the each node. The one that is 1 is connected with 5 and 4, 5 is connected with 2 and 3, and 2 is connected with 5 only, 3 is connected with 5 only, and 4 is connected with 1 only. So by using above formula we can get U1, U2 and U3, U3, U4 in this way, in this equation, by using m is equal to 1, n is equal to 1 and k is equal to 1 respectively. So in matrix form ut will be this term and this error. This is error of first bus, second bus, third bus, fourth bus and fifth bus. Therefore dynamic state of charge of the state of charge can be found this way, which is product of b and ut. B is identity, so this will be this one. For first case, let pt is equal to 0.5 with initial state. This one from this reference table we can, with this table we can get the reference SOC for this particular case, and the error will be SOC 1t minus 30, the reference SOC 2 minus its reference, SOC 3 minus its reference, SOC 4 minus its reference, SOC 5 minus its reference, and finally we can get this nice equation, that this term then this SOC plus this term. From this we can get this result for that particular case, that is point pt is 0.56. In this case the state of charge of this first is between the pt is between this one, so the state of charge will be, let's try to yeah, this is between this and it will try to maintain the reference, and this and this. There will be 80 and it will be 65, 60, 30 and 20 respectively. When we want to simulate for whole day, that is time of price is different for each period of time, that is 0.35 for 0 to the 9 a.m. and 0.58 for 9 to this 1 a.m. and 0.75 from 1 a.m. to 1 p.m. to 8 p.m. and from 8 p.m. to 10 it is 0.58, and from 10 to 12 it's 0.35. By using this variable time of use for a different period of time, we can get this result update for each state of charge of the battery for this particular period from 0 to 9. In this case, we can see from this table the PT is 0.35. that means it is between this one, so the charge will be, the state will be, it is less than this, so the battery will be charged to full. And for the second one, same for the second one and third and fourth, and we can see from there then the PT is less than this minimum, so they will be charged their maximum. We can see this, and for this period the PT is 0.58. in this case, the first, from this we can see the price is between two for the first, so the price will remain in between as it is, and for the second the PT is less than this minimum, so it will be charged at maximum, and third it will remain the same, and fourth it will remain the same, and for fifth the PT is greater than this maximum, so it will discharge for the fourth. We can say this, and for this period the price is 0.75, so all of these battery will discharge. We can see 0.75 is greater than equal to this P maximum, so we can see from there, so they are all discharged. And from that 20 to 22 a.m. we can see from here the price is 0.58, so the first, third and fourth will remain the same, and second will charge to it full capacity because the PT is less than its minimum, and for the fifth one the PT is greater than its maximum, so it will also remain it's in its previous state. And for finally we can see from here the PT is 0.35, so which is less than equal to PU minimum, so all of the battery will be charged to its maximum value, we can see in this case. So finally the conclusion, the distributed optimal control algorithm, which is robust to system topology change for energy management of energy storage system in a microgrid. The algorithm only utilizes the information of the local and its neighbors. Therefore, the communication and computation burden is shared among the local controller to avoid the investment of an expensive communication network and powerful central controller. The simulation results are in agreement with the theoretical analysis. The proposed distributed control algorithm is effective to meet the different preferences of all user dynamic under the dynamic electricity price. So we can see from this one. Thank you.